I recommend them all. Yeah, and I also need to tell you the homework, which is due Monday.
Yeah.
I haven't done that either. But I figure no one's working on it yet, so I could be wrong. But anyway, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for these students. Pray that you just help us to use this time to glorify you, Lord. In your name I pray. Amen. So I'll start with your questions. I have solutions I'll show you. But before first of all, so I think it's chapter 6, number 18. It's about calculating an inner automorphism for D4, right? And so I worked on this for a little bit, and I've come to the following sort of dictionary. So here it is. Galian, me. So he's got R90. I'm going to put X. He's got H. I'm going to call that Y. Now this may not be unique, but so in continuing down this path, let's see here. D is equal to xy. V is x squared y. This is not the only possible dictionary, I think, but it's one. Let's see here. I checked it geometrically for what it's worth. And then, of course, you've got like R0 is 1, R180 is x squared, R270 is x cubed, right? So there you go. That's the dictionary to start with. That's the translation between Galian's version of the Dihedral group of order 8 and the way I'd prefer to calculate with generators and relations. So if I'm going to do any kind of calculation in the Dihedral group, I'm going to change it to generators and relations because it's just way easier. Now he tells us that this automorphism rather, is an isomorphism from D4 to D4. What's it do? He tells us two things, right? In problem 18, he tells us that the R90 maps to R90, which in my language means phi of x is x, right? And he also tells us that phi of y is x squared y. Or in Galian's language, phi of h maps to v. But I prefer generators and relations for an actual calculation, which is what this is. So we're supposed to do what? We're supposed to show that this data, right, this given data, and we're given this, and also we're given that phi from D4 to D4 is isomorphism. Supposedly, that is enough to show that phi is an inner automorphism, and in fact it's formed by conjugation by x, or x cubed. I think he just has x in this problem, does he? Yeah, suppose phi is an automorphism of D4 that takes R90 to itself, H to V. Prove that phi is an inner automorphism induced by R90. Okay, so what is D4? D4 is equal to 1x, x squared, x cubed, y, xy, x squared y, x cubed y. That's everything in D4. So I would point out that there's a simple nomenclature that captures these in two foul sweeping cases. These things have the form x to the m. These things have the form x to the m times y. right? So if I can show my claim on elements of those two types, we are good to go. So first of all, check it out. Phi of x to the m, right, is what? By definition, it's an isomorphism. So by what we worked out the other day, that's phi of x to the m. But hey, phi of x was given to be x. So this is x to the m. And if you tilt your head and squint, you can see that that's x to the m, x inverse, right? By laws of exponents, yeah. And so there you go. That is phi, the automorphism, inner automorphism induced by x, acting on x to the m. As you can see, the mapping phi agrees with the inner isomorphism induced by x for this half of the dihedral group.
You can do it generally because that works for any number.
Yeah, this is true for m equals to 0, 1, 2, 3. Yeah. Likewise, if we calculate phi of x to the m y, right? Well, this is an isomorphism. So we have the homomorphism property. This is phi of x to the m times phi of y. But we have the isomorphism property, the lemma, the power pull the powers out property, right? So that's the phi of x to the m times phi of y, right? Again, all I've used so far is that it's a homomorphism, and it also, this is just, I haven't used the data yet. Now I use the data. I mean, I've just used that it's an isomorphism so far. Now this gives me x to the m. And phi of y, what was phi of y? Phi of y was x squared y. Now I'm trying to show that this is an inner automorphism, right? How to do this? I mean, there's various ways to proceed from here. Let's see here. See, what I want to do, my target is to have, what I want, right, is I want x to the my, x inverse, right? That's what I'm after. X inverse here is x cubed, though, right? So there are various ways you can go here. I think what I'm going to do is be lazy. I mean, this is the way that's occurring to me right now. I'm going to say that's x to the m, x squared y. And there's always a simpler way for those who see differently, but I can add an x to the fourth here without loss of anything, because that's the identity. And then I can just keep the x cubed I want, right? So this is going to be x to the m plus 2 y x cubed. If I commute these, I get an x inverse.
Shouldn't that be x to the n plus 1?
Yes, I think yeah. Very good. It would have been painfully obvious very soon. So that's x to the m plus 1, x inverse y, x inverse, because x cubed is x inverse, right? And so that is exactly x to the m, y, x inverse. In other words, it is phi of x acting on x to the my. And there you go. That's the other half of the dihedral group of order 8. Because m equals to 0, 1, 2, 3 covers the other half of the dihedral group.
How does the thing work? Or why can we commute?
We don't commute. In fact, it does not commute. Yx is equal to x inverse y, going back to our previous work in the dihedral group.
Okay. Oh, yeah.
I use that to take this pair and change it to that pair. I suppose if you were really greedy, you could try to do this all at once using like y to the k times x to the m, right? So but I was a little bit nervous to do that, so I decided to do it like this, you know? Yeah, I mean, the main thing is this notation. Come on. My brother's like, he always asks students after that, like some students really like this way of doing it. And for those students, he always asks them something like, okay, what's your notation for D5? It's, yeah, I mean, this is kind of okay for D4, but past that, good gracious, it's awful. Although I think Rotman has some kind of systematic nomenclature for it, but whatever. It's Rotman. Is that good? I'd rather not go into how I arrived at the dictionary. It's just stupid, gory, hand-to-hand. I said R90 is X, and then I studied what had to be Y, as is just looking at the products geometrically. Someone else pointed out that they're in the same order. Just assume that the order matched the order in the book. And like that happens to also be legitimate, but that's an accident. So they're lucky. They know who they are.
Well, you know that R0 has to be 1 because R0 is the identity, 1's the identity.
Right, that's not up for grabs. And you know that you can't use x equals to R80. So x either has to be R270 or R90, because those are the two elements of order 4 in here. So that's kind of not up for grabs. But I think you could either make H be Y or you could make V be Y. So I'm not sure if you could make D be Y. I haven't thought about it enough. There are some choices here. I don't know all of the flavor choices, but this is a choice, and you can use it. So problem 27 was the other one you had a question about. Problem 27, I was actually planning on lecturing on, but it just never quite gelled yet. This is an important problem. I like this problem a lot. It really, I mean, we get sucked into just talking about Zn and Un so much in here, partly just because that's kind of the thrust of Galilean. But matrix examples are important, and this is a really great one. So number 27. So basically here, we're going to explore the connection between 2 by 2 matrices, A minus B, BA, such that A and B are real numbers, right? Versus the complex numbers. And this problem basically asks us to show two different notions of isomorphism here. Okay. So I'll start out with the additive one. So if we say, in fact, the same isomorphism works for both. But so if I look at psi of, I'll start with the complexes. How about that? So if I look at psi going from, say, the complex numbers to this particular set of matrices, I can define it by, am I not following the book?
It's just a different Greek letter.
Yeah.
Oh, pitchfork. Let's see here. So like psi, as in like when I tell my daughter something, psi. Let's see here. So psi of A plus IB is equal to A minus B, BA, okay? All right, so if you look at psi of, A plus IB plus X plus IY, you get, you get psi of A plus X, parentheses, plus I times B plus Y, right? So that's how we add complex numbers. We add the real parts, add the imaginary parts. Nothing shocking there, I hope. And so that puts a plus x minus parentheses b plus y and b plus y. But this we can rewrite by properties of matrix multiplication, addition, grief, b minus b, x minus y, x, aka psi of a plus ib, plus psi of x plus iy. I'm going to get tired of writing all the details out in this problem pretty soon. There's a lot to write. Nothing is terribly difficult, though. So that shows that this is a homomorphism, right? So psi is a mapping, and to be more clear, so psi is homomorphism of the complex numbers with addition to these matrices with addition. I haven't proved that that set of matrices forms a group under addition, but it does. If you take two matrices of that type and you add them, you get another matrix of that type, right? It's clearly a group. And this is a homomorphism of the additive group of complex numbers to that additive group of matrices. Is it an isomorphism?
Didn't we have basically the same problem in our last one?
I did?
It was similar, just not complex.
Oh. Oh, I think I gave you the corresponding one with rational numbers?
Yeah.
Yeah, that was on purpose. I was saving this one for class. I just didn't get to it. But so what's the kernel of psi? Yeah, so this, like, Blaine asked me to do these Tuesday. I didn't get the email in time. It was a very smart question to ask Tuesday, but my email. Yeah. I did that on purpose. I meant to leave that opening. Anyway, so kernel of psi, what do these things map to 0? The kernel of psi is clearly just 0. Okay? Because if you look at psi of a plus ib equals to 0, it forces this to be the 0 matrix, and consequently a has to be 0 and b has to be 0. The only thing that maps to 0 is 0. And is it onto? Well, if you give me the matrix a minus b, ba, this is equal to psi of a plus ib, so there you go, it's onto. So therefore psi is isomorphism, right? In the additive sense. But it's also an isomorphism in the multiplicative sense. But there I got to be careful, right? Like, in the multiplicative sense, I'm not looking at what am I doing with to check that this is in the multiplicative sense. I want to do what? I want to study. I want to show psi is a map from the non-zero matrices. Oh, excuse me. I did the other way around. The non-zero complex numbers to the non-zero matrices, actually. Right. Here, the identity 1 is equal to E in Cx, right? And so to speak, the identity matrix is the identity in M, let's say. This is my notation, my stupid notation. 1 is equal to E in the complex numbers, and identity matrix is the multiplicative identity in that matrix group. Now, there is something to show there. How do I know that the product of two such matrices is again a matrix of that form? I don't know. I forget what the starting point of this problem is, but that might be something I need to show, right? Is that part of this problem? Show that matrices of that form? No, I mean, right. I mean, I guess maybe he either presupposes that we already know that this is a group of matrices, or that's part of the problem. Depends on how you look at it. If I was to give a test question on this, I would hope I would have worded it. You're given that this is a group of matrices and a matrix multiplication. Show that it's isomorphic to the non-zero complex numbers. But anyway, to prove the proof that it's a group under matrix multiplication is very much related to showing that psi is a homomorphism with respect to the multiplicative structure here as well. So the difference is, right, okay, first of all, I'm defining psi the same way. So the new psi is, in some sense, I should maybe put a psi tilde, because psi tilde is actually equal to psi restricted to the non-zero complex numbers, right? Not technically the same map, it's the restriction of the map. But the restriction of an injective map is still injective. And it just so happens that this restriction is made in such a way that it continues to be onto, right? Could you restrict a surjective map? And I mean, the restriction, right, doesn't change the, see, that's not even quite it either. I don't know, it's, I mean, that's not even quite accurate, because it's not just the restriction, I'm also monkeying with the codomain. I mean, psi tilde is the mapping from this to that, right? So it's worse than a restriction. I'm throwing a point out of the domain, but I'm also chopping down the codomain. But those points are paired, right? So it actually ends up being injective and surjective still for the same reasons, right? Because we still have the onto argument just like we did before, and the kernel, well, what's the kernel now? The kernel's a little bit different. Why is this, now there's something to check here though. Why is this still injective? It's funny, this previous argument still gives us injectivity, but let me give a kind of a native argument here, like a self-contained one. Sorry, less talking, more writing. So the kernel of psi tilde, right, would be what? This would be a plus ib such that psi tilde of a plus ib is equal to the identity matrix. See, that's the identity here. So the kernel is a different thing. The additive kernel and the multiplicative kernel are different, right? So this is what? I mean, so that's A minus B, B, A, right? So what does this tell us, basically? Just what? A equals 1, B equals 0, right? So long story short, the kernel is just 1. Hence, psi tilde is injective. Now again, I'm cheating. What do I have to do before I use this? I shouldn't say that until I've shown something else, which is that psi tilde is actually a homomorphism. I only get to use the kernel implies injectivity for homomorphisms of groups. I have not proved that psi tilde is a homomorphism yet, so let's do that. Psi tilde of a plus ib times x plus iy. All right, so that is psi tilde of ax minus by plus I times ay plus bx by complex number multiplication, which I assume you guys know how to do. And now I apply the definition of the map. The isomorphism, that gives me ax minus by, ax minus by minus ay plus bx, close parentheses. And then what you want to do is meet in the middle on this one, right? So on the flip side, psi tilde of a plus ib, psi tilde of x plus iy, what's that? It's the product of these two by two matrices. Multiply them, what do you get? as you can see, that is equal to psi tilde of a plus ib times x plus iy, right? And also contained in here is, by the way, a proof that this is a multiplicative group, right? At least the closure is right here. See, if I take the product of two matrices in M, I get another matrix of the same form. So M is closed under matrix multiplication. It also contains the identity because that's A equals 1, B equals 0. So it's got the identity, it's closed under matrix multiplication. It's also closed under inversion. You can check that as well, like the inverse of one of these guys. This is pretty cool, guys. Check this out. The inverse of this, we know by the 2 by 2 matrix formula, is what? A squared plus B squared, right? It's really beautiful what's happening here, by the way. Check this out. So there's the inverse by the 2 by 2 matrix formula, right? So this is the inverse image of what complex number? It's the inverse image of a minus ib over a squared plus b squared, which you might recognize, right, as, if you're fresh on your complex arithmetic, 1 over a plus ib. So this isomorphism somehow transfers reciprocation in the complex number system, non-zero complex numbers, to the 2 by 2 inverse formula at the level of matrix multiplication. These are two different notations for the same structure. These 2 by 2 matrices are complex numbers, is what an algebraist would say. Sometimes I think of myself as an algebraist. Oh, anyway, getting back to the problem, this shows that psi tilde is a homomorphism. It's injective. It's still it's surjective for essentially the same reasons, and there you go. You have an isomorphism between the non-zero complex numbers and the non-zero matrices of this type.
Sorry, I didn't get it written down. What was the onto?
Oh, it's really simple. Just pick your favorite point in the codomain, say a minus b, ba, right? And notice that that is psi tilde of a plus ib. So, arbitrary element.
Okay.
It's the image of that. And if that's non-zero, so is this. So there's a little bit more writing to do, but that's basically it. Last problem. So yeah, Blaine asked for 3. These are 3 good choices.
Sorry.
I don't know what's good.
There are 2 by 2 complex matrices which are isomorphic to the quaternion 8 group. I might give you guys a homework problem about that sometime soon. There's all kinds of interesting matrix groups. Like the dihedral group, we can find isomorphic matrix groups that model the dihedral group. 2 by 2 matrices can be used to model the dihedral group.
Use that bottom line.
Hmm?
Can you use that bottom line?
This one?
Yeah.
Yeah, sure.
Or I can, yeah, I could come in. Okay. You
Okay.
can use it.
Oh, okay. Cool. There's a really big difference between those groups we're just looking at and the ones that I was talking at the start. Like D4 has 8 things in it, right? M and C are infinite groups. So they're really quite different animals, you know, but the same group theory describes both of them. So the other one, that's right, exactly. Where was I? 30, what was it? Which one was it?
36.
I mean, I could do 36, but that was, I think 28 was the one. Yeah, I think it was 28. It doesn't really matter, but I'll talk about, I can do both of those. Let me do 20. 28 is fast. So 28, he basically says, look at Rn paired with addition, right? So this is an abelian group with respect to addition. Now, he's got all kinds of clumsy notation he's trying to get us to use. And I'm going to write it down, but I'm not going to use it because it's awful and stupid and the wrong way to denote these things. Because we already had linear algebra, and we're past this. We don't write that for an element of Rn because it doesn't, if it depends on the question, right? But like this, we denote by A. It's a vector. Okay, A is a vector. And so here he says, show that the mapping, and I'm not going to write the mapping the way he writes it. I'm going to write it in a civilized fashion. So phi of A is equal to minus A is, and I mean, he's writing it in a way which presupposes a lack of background in the reader, all right? He's writing it in gory, unnecessary details, all right? So, we're supposed to show that this mapping here is an automorphism of the additive group of Rn. It's called inversion, all right? Automorphism. All right, first of all, is phi a mapping from Rn to Rn? If you multiply a vector by -1, is it still a vector? Yes. Is this, so, you know, suppose here, I'll do 1-to-1. Let me go old school. Phi of A equals to phi of B implies minus A equals to minus B implies A equals to B. Therefore, phi is 1-to-1. Is it onto? Let A be an element of Rn. Note, phi of minus A is equal to minus A is equal to A. Therefore, phi is onto. So, hence, phi is bijection on Rn, right? We'd have it's an automorphism, but we also need to show a preserved structure, right? What structure are we preserving? We're preserving the additive structure of Rn. So phi of A plus B is equal to, this is a really complicated calculation, so watch out, minus, but this would look so much more complicated if I use component notation like he's trying to suck me into. I refuse. This, by linear algebra, or calculus 3, take it with me, minus A minus B, which is, by the way, phi of A plus phi of B. So there you go. Phi is a homomorphism, which is also a bijection, therefore it's an isomorphism, hence an automorphism of Rn. That was 28. Oh, describe the action of phi geometrically. It's inversion. I don't know, I guess he wants more. What's it do? It takes this vector, right? And it swaps it over to this guy, right? So it's like reflection through the origin, I would say. I would usually just say it's inversion, though. So I guess it's kind of circular for me. Sorry. Those are good questions. I wish you'd asked me. I wish I got your email in time last time. It would have been better than what I did. Because I should never have said, I said something to you last time which is incorrect. Our Zn is not a subset of Z. I do not mean to have our Z mod n a subset of Z. That is not what we signed up for. I should not say that. We could define a subset of Z which is isomorphic to Zn. But that would be something else. Like I want Zn to contain equivalence classes. So going back to that thing we did last time, when I write like psi, a mapping from say Zn to the to the complex, well, here, let me make it not be onto, but to the non-zero complex numbers, this is not a surjection, okay? This would be a homomorphism in my current nomenclature. And so I claim a formula. And let me write it more suggestively. What I really should write is something like this. The equivalence class containing the integer j maps to the exponential of 2 pi I j over n. And when I write something like that, to be careful, since I'm working with cosets, actually, j is a coset, j bracket is a coset. In order to show such a function is even well defined, I'm obligated to show you that that formula is independent of the choice of representative. So I need to, it remains, I should show that if, j is equal to j prime, then this is equal to that, right? If that's not the case, then my mapping isn't a mapping. I mean, it's not a function. It's not single valued. And anytime we define a function on a coset, technically speaking, a departure from single valuedness is just waiting in the wings to get us. Here, to give you an example of something going badly, you could do something like this. Phi from Zn to Z by phi of the equivalence class containing j equals to j. Well, this is definitely not a function, you see, because I have j is equal to, say, j plus n, et cetera, right? So phi of j would be phi of j plus n, which would be equal to j plus n. And my use of equality in functions starts to become a problem because it's not single valued. This phi I just wrote is not a function because its output, that formula doesn't output just j. In fact, to be clear, I mean, what is the output of this? This is nz. Sorry, to be more clear, this is actually, well, I mean, you could look at it like that if you want to view that as a subset of z. To be more precise, it's j plus nz. It's the set j plus n times k such that k is an integer. If you want me to be more precise. I mean, that's the image of a single element in the domain. This is not a function because the formula depends on the representative, right? This, on the other hand, does not, because if we look at j prime would be j plus like 2 pi k, right? For some k in the integers. And so when you look at phi of j prime, we get exponential of 2 pi I j prime, right? But what is j prime? J prime is j plus 2 pi k over n. So that's the exponential of 2 pi ij over n times the exponential. This is by laws of exponents, which I probably should make you guys prove. Oh, wait a minute.
I was expecting it on the first test.
Wait a second. This is nonsense. What does this mean? This means that j prime minus j is an element of nz. In other words, kn, not 2 pi. There's no 2 pi in there. It's just integers. Kind of important. All right. So anyway, now we got our 2 pi I k.
Was that the same for step up top? 2.
This? Oh no, that's legit. That 2 pi's got to be there. That's because of how sine and cosine work. So the thing is, the exponential, right, e to the I theta is cosine theta plus I times the sine of theta, right? So if you put theta equals to 2 pi times k for k, an element of the integers, right? Then what happens is that this just gives you cosine of 2 pi k plus I times the sine of 2 pi k, right? That's 0, and this is 1. So the imaginary exponential of 2 pi I k, any integer multiple of 2 pi times I, this is just 1. And of course this is precisely psi of j. Now this is the thing that I was trying to verbalize and I couldn't get out of my head last time, because my problem is I was thinking of Zn as being a subset of Z, which is not what I want to do.
Okay.
Because if I do that, it creates other problems for us. I mean, I don't want to use this notation a lot of times, right? I want to just write psi of j. But I should remember that that's just a shorthand for the equivalence class containing j. Because when we're working with Zn, we're really working with cosets, truth be told. At least that's my viewpoint. So that's the fix to what I did last time. And because to do otherwise, it requires me to start monkeying around with like breaking into cases and looking at when the sum of the two go beyond, right? If I just work with equivalence classes, if I take like equivalence class containing j plus equivalence class containing, k, then I've got the equivalence class containing j plus k. I can just add them and it still makes sense. I have all that modular arithmetic. Anyway, I still should come back and talk more about this mapping at some point more, but that's the next wrinkle. Any other questions, guys? I will say this, I'm trying to hit the major theory in here, and I will, once that's done, come back and start checking off other little, like, things on our bucket list, like classify all the groups of order 4, or, there's all kinds of like little theorems here and there scattered throughout here about pinning down what's possible at various orders, and we're working our way towards that. I'm just eager to get to the main theoretical constructs before I start fiddling around with those kinds of things. I do at times, if they're low-hanging fruit, stop and do them. Like last time we did that, a group of prime order is cyclic because, oh heck, it cost us a minute, right? And it's such a huge thing. It's such a huge thing to know. But anyway, I'm not really following the book precisely. At some point after the dust settles, we will have covered chapters 6 through, 11, and then the bits of the later chapter on Zilow's theorem and simple and solvable groups. But honestly, I'm going to another book for exposition on those things. So it'll be contained in the notes. So yeah, it should be fine. Yeah, I was very happy about number 18. Once I divorced myself from his notation, I was like, oh, this isn't that bad. Because when I thought about it to start with, I was like, oh, this is awful. And I've asked you guys to do like 8 times this in your homework. Oh, you should notice that, I should have done this when we were working on it, but you can pretty easily see that phi of x is phi of x cubed, right? If you use my notation, it's really easy to see that. So phi of x cubed. So if you let's take the hard case. X to the m times y, right? This is x cubed, x to the m y, x, right? Because x cubed inverse is x. And then what you do is just put an x there, and that's x to the m, that's x squared, right? Yeah, yx. And so that's x to the m. I don't know if you noticed this or not yet, but x to the m times y is y times x to the minus m. Well, let's not say m. M is loaded here, right? This is true. And so I can just, that's y, x to the minus 2x, which is x to the m, y, x inverse, aka phi of x, acting on x to the my. And the reason that x phi of x cubed is equal to phi of x is even easier for rotations. It's just straight up laws of exponents there. Because when you conjugate by x, you're putting x on one side and x cubed on the other. When you conjugate by x cubed, you're putting x cubed on one side and x on the other. But either way, you're just adding 4 powers of x on the thing, so they're equal. Because an element commutes with itself, so you can laws of exponents or rearrange it. Anyway. Anyway, thank you for your questions. I think these meetings tend to go better when I actually have preset questions and I think about them a little bit beforehand. So I should stop the tape. I'm excited about tomorrow. Tomorrow we do factor groups. Wahaha.